Welcome to another session of the Wireless Lab course. In this session, we will focus on synchronization. We will build a frame and we will send it and receive it using devices. And once this in MATLAB code, we will not use the already existed softwares on those devices. Now, once this frame is received, we will see how we will extract the data out of it by compensating for both time and frequency offsets. Starting with frame generation and transmission, we have this symbol script where we generate data, any data, and we generate a preamble. This preamble is a duplicated sequence of different lengths. We can change the length by changing these two parameters. You will be given by the TA this function for sequence generation, sequence generation. And as we see here, we have it duplicated. This is the preamble. And now in the frame, we put some guards at the beginning and at the end. And we have the preamble, then the symbols. Now, once the frame is formed, we filter it using a root raised cosine filter. As we see here, we upsample, then we convolve. Now, this wave is ready for transmission. So we set up the SDR's parameters, as we see here, the IPs for both transmitter and receiver, and we have their center frequencies, the transmission power, and the sampling rate. Also, the frame length is required by these functions. Now, these functions sent to key site and received from key site are both given also by the TA, and they accept the sending function, as we see, accept two parameters. The first one is obvious, which is the input signal, which should be our own, not a vector. The second parameter is this structure of parameters. We have to provide these parameters to this function. For the receiver side, we just receive, so we just need setup parameters, which are the same structure as we see here. And the output of this function is the received signal here. Now, in both functions, there is an output which is radio. It's used to stop the connection to both either transmitter or receiver. Before starting the synchronization algorithms implementation, let's see the steps that we will go through in this block diagram. These blocks with red stars are mandatory. Also, we have to do them. Also, those green starred boxes are mandatory. But if you did this one, you don't need to do this one, and vice versa. This one with the yellow star is performed only for a special case, as we will see now. Now, as we know, we generated a frame with some guard bands, so the frame has an edge that has to be detected roughly at this step here at the very beginning. There are two methods to do this. One is energy-based and the second one is correlation-based. We will discuss both of them later. The second step is cross-frequency offset compensation. We do this step for signals for low-end equipments suffering from severe frequency offset values. Because if I didn't do this step, I will not be able to do match filtering. The signal will be distorted and signals will not be matched anymore. So I have to reduce the severity of this offset value. And this is especially the case when I operate at low sampling rates. Now, once I did match filtering, I go to this step here, which is fine frequency offset compensation. I almost eliminate the whole frequency offset value. Now, I can skip this step, as we said, and do it here later after time synchronization. Or I can do it and skip this one. We will see and discuss these options later. But here, this method relies on the duplicated sequence we just generated. It's like comparing them and telling what's the offset value. We will discuss it. Now, still I have samples here, and as we know, within a group of samples, I have to pick only one that represents the sample. And this is achieved here in time synchronization, and there are some steps here in this at this stage. We will see them. It's sample and sample synchronization. Also, we can say that edge detection is part of time synchronization. So time synchronization is achieved here and here. Now, after getting the samples, if I didn't do this step here, I have some frequency offset that need to be compensated. So I can do this at the sample rate here, and this method is FFT based, and it's very similar to this method here. We will discuss it and see it. We will see both methods, the coarse and the fine frequency offset compensation methods here. Now finally, once I have the samples, the constellation, if I look at the constellation, it will be rotated because of phase ambiguity. So I will fix this ambiguity in a very simple way, as we will discuss later. Now, starting with the synchronization algorithms, we have them all implemented in this script. As we know, we generated, sent, and received a frame using the code we discussed earlier, using the devices. I have sent and received a signal stored in this structure. I just load it using load function, and inside it I just have one variable, which is signal Rx. Let's see this signal in time domain by uncommenting this line of code. This is the signal. The receiver is adjusted to capture a burst with time equal to the time over 3 frames. As we see here, this is 1, 2, and a portion of this frame and this frame, which together is equal to the time of 1 frame, in addition to the gaps for sure. Now, since they are identical and I'm only interested in the synchronization process itself, regardless of the data, let's capture manually one of them. We can say roughly from the time index 12,500 to 21,000. I just need this portion of this signal, which is something I did here. Let's uncomment and see it. So this is the frame. These are the guard bands, and this is the duplicated M sequence corresponding to the preamble, and here we have the QAM modulated data. Now we have the signal. Let's move on to the edge detection, which is the first step. In edge detection, as we said, we have two methods, correlation-based and energy-based. For correlation-based, I have to generate the preamble locally, upsample it, and convolve it with a filter that is identical to the one used at the transmitter site. So I have a signal that is identical to the one received. So I just do correlation and find the time index at which the edge, the frame edge is located. So this is how we do the correlation-based edge detection, which is something you will do at home. Here we will show you the energy-based method, which does not require the preamble, as we see here. Let's go to the implementation here. So I have a window for averaging. Its size is 16 samples, 16 times the oversampling ratio here, because we are working with samples. Now, this is the signal. We are interested in the absolute value of the signal. We just want to see how the envelope of that signal is changing, because the energy-based method is based on the abrupt change of the signal level, moving from the noise floor to the signal level. So I will do averaging with a window size of 16 samples to smooth the curve of this signal. And I will take the derivative of this average signal to see the peak at which we have this abrupt change. So let's see this derivative. I will just plot signal. Let me stop this and run. And this is the derivative. And here I have the peak corresponding to the starting edge of the frame. Here I have also another peak, as we see, with the minus value, which corresponds to the falling edge, the right side edge of the frame. Its slope is minus because it's moving from high value to low value. So this one will correspond to the starting index. As we see here, we just pick it using this code here, and we multiply it by the window size because we did the averaging. So this is the index. Now let's see the selected time index and on the frame itself. We can plot it here as we see in this code part. We just plot the frame again, and at the time index, the selected time index obtained by this function, we just plot a marker showing the selected edge. So let's run the code again. As we see here, this is the frame we saw earlier, and this is the estimated edge, as we see here. Next, we move to the coarse frequency offset compensation, which is only applied for low-end equipment with large offset values. We don't apply it for high-end equipment because their offset value is small, so I can do match filtering, and after match filtering, I can do the frequency offset compensation only one time, and having this implementation here is just an additional complexity. Even worse than that, I might add additional offset value if I perform it here before match filtering, because as we will see next, this method is an FFT based, and in the frequency domain we have samples with some resolution that depends on the FFT size. If the offset value, the small offset value, is between samples, I might make a wrong estimate that adds additional offset value to the original value when I do compensation here. So we just do it for low-end equipment. Let's see how this method works. Here I have the signal. In this function we implement this method. It takes a signal, which in our case is the preamble signal, and it returns the offset value, and I compensate for this offset value using this simple code. Now, how do we pick the preamble? We have the signal, and based on the estimated edge index, we decide the starting and ending point as follows. The starting point is the edge itself plus some guard symbols to the right to ensure that I'm inside the frame. And the end index, again, the starting index plus the preamble side minus some guard symbols to the left to ensure that I am inside the preamble signal. So this is roughly the preamble signal. I take it for coarse frequency offset estimation. This method is as follows. Now, we take these samples and we raise them to power m. Now, if you have a signal, m is the modulation order here, and since the signal here is an m sequence, which is binary signal, m will be 2. So I raise it to power 2. When I raise it to power 2, it will be a DC signal with no information. If I take the FFT of such a signal, I will get a peak in the frequency domain at a frequency of 0. But if there is an offset, frequency offset added to this signal, raising to power m will make this signal multiplied by an exponential, complex exponential with power that is linearly dependent on m times f naught, where f naught is the frequency offset value. Now, when I do the FFT, if I find the peak index, this peak index will tell me the offset value. So once I find this index, I divide it by m, and I get the offset value. And this is what we are doing here. We just take the powered signal, we take the FFT, we get the samples in the frequency domain, we define the frequency axis, and then we find the peak at the index, the frequency index at which we have the peak. Let's see the signal in the frequency domain, the powered signal. This is the signal, and we have the peak very close to the zero because, as we said earlier, low-end equipment has very small offset values. This is a coarse estimate. Next is match filtering, which is a straightforward process. After match filtering, if we decided to go with the frequency offset compensation at the sample rate, we use the duplicated M sequence method, which is a method that you will do at home. We will show you later that method at the sample rate, which is the FFT based. But for this method, you will take the signal, again similar to what we did for the coarse frequency offset estimation method. You will take the preamble, you will find it roughly, and you will find each of the M sequences which are identical. Then you compare them sample by sample, and you have to know that between each sample and the identical sample after some time in the second preamble, there is a phase increment that depends on the frequency offset value. Based on this dependence that you know and understand, you can estimate the frequency offset value.